have them recorded and uploaded. What would you like to know about anything? Who's got questions?
Could you do one of the problems from the review?
Yeah, from the review. Sure, Kayla. Which one?
3B.
Which one?
3B.
3B. Oh, yeah. So 3B is a good one, right? Now, I sent out, I think a couple of weeks ago, you'll have it. It's also in the textbook on page 632. But I photographed and sent out this table that shows like a whole list of test methods you can use. Lots of times, more than one test method can be used. You can do it by the integral test. You could do it by the alternating series test or something like that. And sometimes you'll notice lately, I've been doing what I call a verbal test method. We've just been using some logic. You can use that if you do it correctly. So if you want to decide if a series converges or diverges and somehow explain it like in a written word, make sure your explanation is like textbook kind of thing. So 3B is one of those. So let's look at 3B. So 3B. Oh, geez. Thank you. And I see that. Wow. You know, I've been good with that. And then sometimes I just totally forget. It's all Michaela's fault. She distracted me. Okay. So 3B, 3B, there we go. So from n equals 1 to infinity, and we have 1 over n squared minus 2 to the n minus 1 over 2 to the n. Oh, wait a minute, I got a couple other people coming in here. Wait till folks get in here. Hello, everybody. So for the few of you who just popped in, we're just going over the review sheet tonight and I'm answering questions. So 3B. So the first thing I'm going to do is do some algebra to this term over here. So 2 to the n minus 1, that just turns into 2 to the n times 2 to the n minus 1, and that turns into 2 to the n times 1 over 2. So this reduces to 2 to the n, and then that 2 goes to the bottom. Next, these 2 to the n's now cancel out. And it leaves us with that. Now, this series consists of 2 terms separated by a minus sign. So we can look at each one of those separately. And the reason we can look at each piece separately is, so infinite series in some sense are also what an integral really is. So if we had an integral, for example, that was 1 over x squared minus 1/2 dx. If you were to integrate this, you'd integrate this one, and then you'd do each of these integrals separately. So we can do the same thing here. This piece, let me use colors. This piece converges. This is a P series. In this case, the power is equal to 2, and 2 is bigger than 1, so that converges. So that piece converges. This one, there is no n. So n is 1, 2, 3, 4, 5, 6, 7, 8, 9. This just stays 1/2. So this diverges. This just looks like 1/2 minus 1/2 minus 1/2 minus 1/2 all the way out to infinity. So this goes to negative infinity and diverges. So this term converges, this one diverges. And so because this piece diverges, the answer to 3B is that series diverges. So let's see, Michaela, is that okay?
Yeah, for some reason I didn't know what to do with like the constant.
2 to the n minus 1?
Yeah, like the -1/2.
Oh, so this just means this is forever, each term is forever 1/2. So
Okay.
you can see that. Another way to say it is, as n goes to infinity, this is 1/2, it's not 0, so it fails the nth term test. That's another reason to say it diverges. That was a good question to ask. Who else has any questions? Anything? No questions, going to be real short because I don't really have anything to plan. A whole bunch on there. Anybody want to see any of those? So the test that I'm going to send out, there's 3 or 4 questions where you have to explain something in your words, own words, like number 1 on the review sheet, some things like that. There's going to be some regular series for convergence, divergence, and some power series. And it's certainly not going to be as long as the review sheet. This review sheet is, well, I guess it's not, well, it's not going to be as many questions as the review sheet. Question 4C. Question 4C. All right, let's look at 4C. Oh, that one looks really ugly, right?
Just a quick question. Is there going to be another test on chapter 10, or is that the last test?
Well, the last test will be chapter 10.
Oh, okay.
And there's not going to be, we don't have a whole lot of days left. So chapter 10, there's just a couple of things that I'm going to do in chapter 10. So that one will be relatively short. All right, by request, 4C. All right, so there it is. Now, so this is a power series, and we know that because we have the variable x in here. So this series will converge. The center of this series is -1. The center is -1 because when x is -1, it makes this 0. And once this is 0, the whole series is just 0 plus 0 plus 0 plus 0 plus 0. So that's why a series always converges at the center. Our job is, can we make that, expand that and get more? So we go right to the ratio test. Because of these absolute value signs, when you do the ratio test, you completely ignore this. All we're looking at is this. The only time we use these is if we have a finite interval of convergence and we have endpoints that we need to check.
Can the factorials be simplified beforehand?
Yep, you can do that. Oh, absolutely, you can do that. I just tend to just do it this way. So you can do whatever you want that's legal. So now we carefully replace all these n's by n plus 1. And here, when we do n plus 1, we get n plus 1 plus 2. So that gives us n plus 3 factorial. All right, oops, and absolute values. Now, here comes all the canceling out. With a ratio test, there's always canceling out. And you will always be left with an x to the first on the top. So down here, that x plus 1 to the n cancels out that one and just leaves us with a single x plus 1 on the top. Right here, n plus 3 factorial is n plus 3 times n plus 2 factorial. That's how they cancel out. So this cancels out with that. And there's one more. I know this is messy because I don't have enough space to do here. Here we have n plus 1 factorial. That becomes n plus 1 times n factorial, which cancels out with that one. So what we're left with is we're left with n plus 1, x plus 1 to the first over n plus 3, I think. Did I miss something? No, I don't think I missed anything. So we're left with that. I know that's a little messy, Rebecca. I hope the colors help, but you okay with what I did here, all that slashing? Okay, good. Yeah, just a little. So now I have to pull this back. So what we need is to make all of this less than 1. And we can do that by choosing our x values. Now, as n goes to infinity, and here's what I mean by a verbal argument. As n goes to infinity, that plus 3 contributes nothing. It just turns into dust and evaporates, right, really quickly. When n is 100 million billion trillion, that plus 3 is pretty much invisible, and same with this. So these cancel out. And now we need the absolute value of x plus 1 to be less than 1. So that means to say the absolute value is less than 1 means that we're in between -1 and 1. So this is, and now we solve for x. So to solve for x, we subtract 1. So here we get -2. We subtract 1, and we subtract 1 again, and we get 0. So this is, that's the interval of convergence. And what number is exactly in the middle of -2 and 0? What's the number? Yeah, -1, right? So there's the center. That's right in the middle. That's why it's called the center. Okay, so here's a partial solution. Your answer to a power series question is a picture. Where am I here? Oops. There's the center on the x-axis. So here, we converge. All of these x values will make this series add up to something. Don't care what it is. All you need to know is it adds up. We think of that as being stable. But not equal to, strictly in between. Beyond these, all the x values outside that interval will make that shoot off to infinity. Or now, diverging doesn't always mean go off to infinity. Diverging is also if you just keep bouncing and you never settle down. That's called an oscillating divergence. So the question we have to answer is, what does that series do at the endpoints? And we talked about this a bunch last time. When ice goes from a solid to a liquid, and things of that nature. So to determine that, we have to plug these two numbers in for x and see what happens. And that's where this will come into play again. So I'm going to do this on another board, so I don't have to erase this. So that's the partial picture. Now here, at the endpoints, we're either going to have a round parentheses or square. So round means converge, square means, or sorry, diverge, square, converge. So I'm going to switch over to my next whiteboard. Can't keep track of all my markers here. I think that was it. Is that it? Yeah. Okay. So first we will look at the left endpoint where x is -2. So we put -2 in here. We put -2 in here. -2 plus 1 is -1. So we get -1 to the nth power. And over here we get n plus 2 factorial. So I'll pause there if anybody's got a question. Now, here I'm going to algebraically cancel these out right here. So n factorial over n plus 2 factorial, that becomes n factorial over n plus 2 times n plus 1 times, times n factorial, which is what John was saying earlier. When we started this problem, we could have done algebra to this right away. The n's factor out. So this just leaves us with, on the bottom, n plus 2, n plus 1. And on the top, here we have -1 to the n plus 1, and here we have -1 to the n. So n plus 1, one of those is always going to be odd, the other one is always going to be even. So when we multiply these together, they are always going to be -1. So our top becomes just -1. And now we can see that converges, because on the bottom, if we multiply this out, we get an n squared. We multiply this out, we get n squared plus 3n plus 2. Because of that n squared, that converges because it's a p series. 2 is bigger than 1, that's a p series. And these two terms make the denominator even bigger. So this is going to converge a little faster than that. So at the left endpoint, we converge. Now we check the right endpoint. If we check the right endpoint, that's where x is equal to 0. So if we put 0 in here, we just get 1 to the n. We get all of this stays the same. So we would have -1 to the n plus 1 right here, and then we would have 1 to the n. So this just stays an alternating series on top, but the denominator is still n squared, so it also converges at the right endpoint. So our final answer to this question is so I use a square bracket to say that it converges at those numbers. And that would be the final answer to that question, would be that picture. So, Rebecca, is that okay? Okay, just out of curiosity, what part were you uncertain about? Oh, it makes it really awful. It still works. Right. Oh, oh, so it's just like an arithmetic mistake. Yeah, yeah. So the rate. Oh, okay. So round brackets. So if you have this, and it depends on your mathematical genealogy where you've been before. So if we have something like this, and I put a round bracket, that means as close as you want to zero, but not zero. And then, and some people use this, and it's okay if you have that. Some people use an open circle to be a round bracket and a filled in circle to be a square bracket. So if you're used to those, you can use them. I can handle all of it. And also, when you're doing the ratio test, that's why those absolute value signs are there. You just completely ignore all of this. It works even if you do that, but it makes it way more. It's already messy enough, right? Good question. Who else has anything? Anything at all? No, I don't really have anything planned. I'm just going to answer questions tonight.
Could you do 4A?
4A? Yeah, sure. So, I'm sorry, what?
Oh, I don't know if I was just doing it wrong, but I couldn't get I still had a factorial when I went to take the limit, so I didn't know.
Okay, so let's look. So one mistake I see in power series in general, I'm not just talking about you, Mikkel, is replacing n by n plus 1 not correctly. So let's look at 4A. Okay, so there we are. Oh, did I do that right? Yes, I did. Okay, now in here, the center is 0 because that's x plus 0. So the center of this is 0. And now, before we even do the ratio test, we can simplify this. And this is a different way to do it. So we can do this. So 2n factorial over 2n plus 1 factorial. That reduces right away to 2n plus 1. Now, if we subtract 1, the next number would be this. So then we would have 2n factorial right there. So these cancel out right away. So I can rewrite the series as this. All right, so we okay so far?
Yeah, I think I didn't cancel that out, so I think I made it really difficult, and that's why I ended up messing up.
Well, it just got really messy, didn't it?
Yeah.
Yeah. Well, it's good for you. It builds character to do something like that. Now, if we go to the ratio test. Oh, so as I've said probably many times in here, the most important skill you can have as a mathematician is to be lazy. Do as little work as possible. Anything you can do to simplify a problem before you even start to solve it is a good thing, right? Mathematics is one of the rare things in life where you're considered brilliant if you're lazy. You get credit for being lazy. It's wonderful. So we get x to the n plus 1. Now, when I replace this n by n plus 1, we get 2 times n plus 1 plus 1. We don't just make this a 2, and that's a mistake I see a lot. It's the n that gets replaced by n plus 1. So this will give us 2n plus 3 on the bottom. Then in the ratio test, we divide by the original's term, but dividing by this means that we flip and multiply. So this gives us 2n plus 1 over x to the n, and that leaves us with limit n goes to infinity. Well, these cancel out because that plus 3 and 1, eventually these just look like 1. This n knocks off one of those, so we're just left with x. This has to be less than 1 to converge, so our interval looks like this. And that's our convergence, and the center, 0, is right in the middle. It's halfway between those two numbers. Okay, good so far?
Yes.
Okay, now because we have a finite interval, we actually have endpoints, we have to plug them back up here. But we can use this, because this is algebraically equivalent. So we don't even have to use the messy one. We can just plug these into here, because we're allowed to be lazy as long as it's legal. So if we look at the left endpoint, x is equal to -1, we end up with this series. We get -1 to the n over 2n plus 1, and that converges because it is that converges by using the alternating series test. This is alternating positive, negative, and because the denominator keeps getting bigger, each term gets smaller, so this converges by the use of the alternating series test. So here we converge. When we look at the right endpoint, x is equal to 1, that just gives us this. If x is 1, we just get 1 over this, and this diverges. It diverges because down here, the power, the exponent on the n is a 1, and so a p-series converges when that number is 1. So it diverges at the right endpoint. With an exponent of n to the 1, they converge when they alternate positive, negative, positive, negative, positive, negative, but they diverge when it's equal to there. So our answer to number 4A will look like this. And here's the center. So we will have and all of those values. So that's the answer to number 4A. So I guess moral of the story here is simplify first if you can. I'm sorry, were you going to say something? Sure it is. So you thought there was no exponent? Yeah, there has to be an exponent. Oh, I see. Yeah. So there's an exponent on the 1. Everything has an exponent. If you don't see it, it's a 1. That's all about being lazy. Well, you know what? If it's a 1, we're just not going to write it. It takes too much work. I mean, mathematicians are so lazy. The trig function, the sine, S-I-E, S-I-N-E, well, let's be lazier and make it only 3 letters, right? Let's see, Michaela, 4A, that was a good one. Anybody got anything else? Just to go through it, so number 6, that's called, for problem number 6, that's called a telescoping series. Telescoping series, if you want a number 6, to find the sum of that, this table of methods tells you how to calculate the sum of a telescoping series. Number 5 is just plugging in those numbers and subtracting. There's no converging or diverging going on there. And number 7 is to write down those 5 terms and just add them up together. There's no big things going on there. All right, anybody got any other questions? Just glancing here, problem number 3A, the one with the e to the negative n cubed, that's solved by an integral test. So 3A is an integral test, and the integration is done by u substitution. So what else we got? Any other questions or?
Just a question about the methods in general.
Okay.
For alternating series tests and integral tests, why does the function an have to be decreasing?
Oh,
just out of curiosity.
So the first one, so alternating series test. I'll answer this 2 ways. The alternating series test requires 2 things for convergence. So the alternating series test is a yes-no test. It'll tell you if it converges, tell you if it diverges. The first thing is the terms have to go to 0, but that's true for any converging series. That's the nth term test. If you have adding up an infinite number of numbers, they have to get so small they turn into 0. Otherwise, you're going to add up, just keep getting bigger and bigger. The second thing is the terms, this term has to be bigger than the one that comes right after it. If your alternating series does both of these things, you converge. If it doesn't do it, one of those, you diverge. So why do the terms have to keep getting smaller? And the word is eventually. Maybe they get bigger for the first 100 million terms, but eventually they have to keep getting smaller. So John, I'm going to draw you a picture. Here's the x-axis. X is equal to 0. And instead of thinking of an alternating series as a positive, negative, let's think of alternating series as up, down, up, down, up, down, like something bouncing, right? So if we're bouncing up, down, a bouncing ball, and each of those bounces gets smaller and smaller and smaller, you see eventually it stops and becomes 0.
Mm-hmm.
That's why. That's a picture of the alternating series test. And if you want to think of an alternating series test in terms of positives and negatives, so let's say here's the center. Well, let's say this is 0. So over here, so we'll think of this way as positive and this way as negative. So we converge. So alternating series now means going back and forth. And so going back and forth, and the terms have to get smaller. So if we go back and forth, back and forth, back and forth, and the back and forth keeps getting smaller, then you converge. So 2 pictures of why this is all you need for an alternating series.
I'm just curious that if 1 is true, then will 2 always be true as well?
No, no. If you have a series that converges, this always has to be true, right? That's the first test you should apply. But you can have an alternating series where the terms don't keep getting smaller. They maybe keep getting bigger, or maybe they go up for a while, they go down, they go up, they go down. So this doesn't have to be true for a series to be alternating. Let me just give you like an example. I can't think of one offhand. So let's say -3 plus 7 minus 2 plus 9 minus 11. You see that's an alternating series. Terms aren't getting smaller. They're kind of up and down and up and down. So that's, if we keep going in that manner, that's not going to do it. Here's a classic alternating series. That's what the infinite series, so starting at n equals 0, -1 to the n. It's 1 minus 1 plus 1 minus 1 plus 1 minus 1. This is a very famous series. You might think that adds up to 0, right? You think, well, 1 minus 1 is 0, 1 minus 1 is 0, 1 minus... You might think this adds up to 0, but it doesn't. Can you see why this does not add up to 0?
Because it would just keep on oscillating.
It would, but don't the ones, so the ones and positive ones are right next to each other. Don't you'd think they would cancel out, right?
Also, its limit would have to be like, it wouldn't be 0.
The limit won't. Plus, the only way this would add up to 0 is if there was an equal number of negative ones and positive ones. And to do that, we'd have to know what the last number is, but there's no last number. But a long time ago, back in the 1200s, there was I think his name was Saint Ignatius. I think I got the name right. He used this as a way, well, it's a long story, but he used this sort of thing to show that God really exists. He thought he had a mathematical proof for the existence of God. He was wrong. Well, he was wrong about the math. Let me just leave it. The math wasn't right. So yeah, so that's how the alternating series works.
Actually, my curiosity was more like, if the limit is 0, right, then does it have to be decreasing?
Oh, so if the limit of the terms go to 0, do they have to be decreasing? Eventually, yes. So the terms have to go to 0, but that doesn't mean that each term necessarily is smaller than the one that came right before it. Right? So the terms, you can have something that looks like this. But if eventually, so I'm alternating here. So this is the x-axis. So positive values, negative, positive, negative. You can also have 7 negative numbers in a row, 1,000 positive numbers in a row, in which case it wouldn't be like truly alternating. I can't think of an actual example that gets to your question right now.
Oh, I see what you're saying. Yeah, thank you. This had like trouble imagining it in my head.
Yeah. So a truly alternating series is each term has to have what's called opposite parity. Positive, negative, positive, negative, positive, negative. But you can have a series that has lots of positive and negative terms, but they don't happen in order. Does that make sense?
Yes, it's kind of like irrational numbers, kind of in a way. It's just like this never really has a definite.
Right. So you need some other method. Just this. Now here's something very important. The nth term test. The terms of your series have to go to, that always has to be true. But that's not enough, right? That's the whole thing I did with being in a room with no windows and whether it's cloudy or rainy. To get a driver's license in New Jersey, you have to be at least 17, right? But being old enough doesn't mean you get a driver's license. There's a bunch of other stuff. If you're 15, that's it. You don't get a driver's license. Forget it. Go home. But if you're 17 or older, that doesn't mean you do get a driver's license. It means, okay, you've gotten past that step. Now we got to see some other things that go on. Yeah, you can get real philosophical with some of these because in the end, nobody really understands infinity. Not really. It's too much. The human brain can't do it. So we think we do. We have these terms like forever and eternity, but we don't really know what that means. But yet there it is. So interesting questions. What else we got? Anybody?
I just have a question about the integral test.
Okay.
How would an integral diverge?
Oh, sure. So when we talk integral test with series, we are talking and this is just some constant. we're talking improper integrals. That's what this refers to, right? So when you do the improper, you do the integral. And I'm using capital F to mean the integral of that function. And then we treat this like a definite integral. So from here, we would go to, you would plug infinity in, and then minus, just like a regular integral, right? If this was a 2 and this would be 5, this would be the integral of 5, the integral of 2. So this, that's just going to be a number. That doesn't matter. So to answer your question, Michaela, once you put infinity in, well, then maybe it diverges, maybe it converges. You have to look at each one of these independently. So if your integral was, let's say e to the x, right? And this is some constant. Well, the integral here would be e to the x, and then you'd get e to the infinity minus e to the constant, and this, e to the infinity is infinity, so that's it. This whole integral diverges.
Okay, I see. Thank you.
Yeah. And the thing about the integral test is the series that you're using it on, the integral and the series both do the same thing. If the integral converges, the series converges. If the integral diverges, the series diverges. So that's a yes or no test. And that's also on that table that I sent to you. That was a good question. Anybody got anything else? Going once? Going twice? Three C. I don't see. Oh, that's 3A. Right? 3A. Yeah, sure. Since Mikhail, this is a good time to do it. So for number 3A, we're looking at this integral. You replace the n's with x's and we have this integral. So here we have u is equal to negative x cubed. Oh, we haven't done u substitution in a long time. This seems like stuff from prehistoric ages doing integrals, doesn't it? Then we do du, and that will give us negative 3x squared dx. So that will give us negative 1/3 du is equal to x squared dx. So our integral now becomes this, negative 1/3 of the integral to infinity of, where am I here? Oh, e to the u du. So this integral becomes this, and the integral of e to the u is just e to the u. So we get negative 1/3 e to the negative x cubed, and we're going from 1 to infinity. Okay, so far? All right, now, this is a negative exponent. They can trip you up. So this turns out to be negative 1 over 3 e to the x cubed, and then from 1 to infinity. So I sent this down to the basement where it belongs. Now, when we put infinity here, we get negative 1 over infinity plus 1 over 3e. So there's the constant. Well, negative 1 over infinity is just 0. So that means our original series. So 3a converges by the integral test. Very good? Yeah, it's just been a long time since we saw an integral, hasn't it? Remember disk and washer and shell and all that stuff? Wow, that really seems like a long time ago, huh? arc length, all that good stuff. So that's a good question. Okay, what else? Anything? All right, I'm going to hit the record button, stop the recording. So I'm going to send out the test in the next, I'm just going to proofread through it once more.